All right, let's get ready for your evaporative cooling lab. So hopefully you did the reading at the top here, but let's go through it together in case you didn't. It says a substance absorbs energy as it evaporates, which makes sense because if you need to go from a liquid to a gas, those molecules need to gain energy because they're moving around like crazy as a gas, and they were kind of just moving more slowly as a liquid. So when something evaporates, that means it's stealing energy from its surroundings. So the surrounding area gets colder. You can use this fact to measure the rate and extent of evaporation of a substance. If something evaporates really fast, then the surroundings, like your thermometer, are going to have an extreme drop in temperature. So in this experiment, we're going to use a temperature probe, and we're actually going to be using a cotton ball, not a piece of filter paper. Just a little change in the procedure there if this is an older version that you have. And we're going to be squirting 1 milliliter of each type of liquid on the temperature probe, and for the next 90 seconds you're going to look at the temperature change that happens as that molecule evaporates. If something evaporates really, really fast, that must mean that the molecules don't really care about each other, so they must have weak forces between them. But if your molecules have really strong forces with the other molecules of that type, then they're going to want to hang out together in that cotton ball and not want to leave. Number 1, after reading the procedure, hopefully you saw that there are some safety concerns that we need to be aware of in this lab. For example, the compounds are very flammable, so you would not want to light a match nearby. Maybe some of you would, but you definitely should not do that. Also, some of these compounds that we're using are poisonous, so you would not want to touch them with your skin, and you'll want to avoid inhaling them. So don't stick your face right above where they're evaporating. Draw a schematic showing what evaporation looks like at the molecular level. Okay, so let's draw some water molecules because they're really easy to draw. So I'm going to draw a bunch of them hanging out very close together in my picture here. Okay. Alright. As they turn into a gas, they start moving faster and further apart. So in my own words, I would say they are gaining energy and eventually the intermolecular forces between molecules break, and they fly away from each other. Right? Because in order for these molecules to get away from each other, the intermolecular forces, the attractions between them, need to get broken. What is the purpose of the filter paper, or aka the cotton ball, in this experiment? Its purpose is to soak up the liquid so that it will evaporate. Otherwise, it would evaporate so quickly off the temperature probe, there just wouldn't be enough of it to have a good data collection. How should you remove the cotton ball and the rubber band? Should you touch it with your fingers, is what this is saying? No. You should remove it with a paper towel. And we're actually going to put these in the fume hood because otherwise the garbages will be really stinky with leftover liquid. If something evaporates quickly, what will you see with the temperature readings? You would see the temperature drop quickly. If something evaporates really fast. How does that compare to something that evaporates slowly? If something is evaporating slowly, just as you can imagine, the temperature drops slowly as well. What type of molecules would stick together better? Polar molecules or nonpolar? Explain why, draw a picture. Hopefully you are thinking polar, because polar molecules, like H2O, for example, have these partial charges that attract them to other molecules of their type. So for example, check out my H2Os. These O's are really greedy, so they have partial negatives, leaving the hydrogens with partial positives. So now, the hydrogen of one molecule will attract the oxygen of another. So these molecules would like to be together. So would you imagine that these are going to evaporate very fast? Well, they love each other and they want to stick together, so no. So what type of molecule would evaporate fast? The answer is a nonpolar molecule. They aren't as sticky because they don't have partial charges. So they're not sticking together. Alright, in this lab you're going to be testing out 3 molecules. Draw the structure for each, determine if it's polar or nonpolar, draw a second molecule next to your first one, and label the type of force that would occur between them. Alright, so let's draw pentane first. C, 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 with all of our H's, 12 H's. Carbon has an electronegativity of 2.55, and hydrogen is 2.10. That means it's basically a tie. So there are no partial charges on that molecule. So let's draw our second pentane over here. Okay, pretend I drew hydrogens on all of these just to save time. Because these are non-polar molecules, the force between them would be the weakest, dispersion forces. How about ethanol? C2H5OH. I'm going to draw that in its bent shape because it is bent, since there are lone pairs on that central atom. This oxygen is winning against the carbon and the hydrogen, so it's partially negative, leaving the hydrogen partially positive. That means this is a very polar molecule, and another nearby ethanol molecule is going to be attracted to that first one I drew. The partial negative on this oxygen will attract the partial positive on maybe that hydrogen. It could attract the carbon too, it just kind of depends on how you draw it. So we've got a very polar set of molecules here, and what's the force between them? Well, they're polar, and do they have an H bonded to an F, an O, or an N? Yes, they do. So the force between these would be hydrogen bonding. How about butanol? Butanol is very similar to ethanol, it's just a little bit longer, so it's a bigger guy. So same thing here, where we've got an oxygen that's winning and has a partial negative, leaving a hydrogen with the partial positive charge. You guys should draw in all your H's too. I'm just not, to save myself a little bit of time here. So the oxygen of another molecule here, butanol, got 4 carbons there, is attracted to this hydrogen in this first one. Oops, this should be a minus sign here. So again, it's polar, and again, this attraction, because it has an H bonded to an O, is hydrogen bonding. Now the question is, does ethanol or butanol have stronger forces between molecules of its type? And if you look back at the notes, it said things that are larger have, and it kind of makes sense if you think about it, if you're trying to boil these, for example, and it's a bigger, heavier molecule, it's going to be harder to boil. So the interactions between butanol, because it's a long chain and it's heavier, are going to be greater, and so it will have stronger forces. Finally, butanone, it says it's a ketone, so I'm going to draw my carbon double bonded to an oxygen on my 3rd carbon in. You could have drawn it, I guess it'd be the same, just flipped. Okay, so let's take a look at this. Is this polar? Yes, it is. This got a partial negative, partial positive, so this would have an attraction to another molecule. Oops, I didn't draw this very well. Okay, here's my other one over here, so this partial negative. So we've got a polar molecule, but does it have an H bonded to an F, an O, or an N? No. So this force here would be dipole, dipole. Medium forces.